I'm going to do a really short introduction to the concept of chemical equilibrium. Many reactions are reversible. Most of the ones we've done so far this year seem to go only in the forward direction or make product. But when a reaction can reverse itself, it can make a ratio of products and reactants. The forward reaction is considered to be the formation of products and the reverse to recreate reactants. When you have reached equilibrium, the rate of the forward and reverse reaction are equivalent. So if you start, notice the graph, so if you start with only reactants, the reactant concentration is going to decline and the product concentration is going to increase until over time you have no net change in the ratio of reactants to products. You are still changing reactants into products. It's a very dynamic process, but there's no net change in the reactants or products at equilibrium. The better definition of equilibrium is when the forward reaction rate equals the reverse reaction rate. Then equilibrium has been reached. The conditions that are necessary to achieve equilibrium are a constant temperature and pressure, and if you have gases, you must have a closed system. So what is equal at equilibrium again? The rates are equal, the concentrations are not equal. They're not changing any longer when equilibrium has been achieved, but they're not equal. Rates are equal at equilibrium. The law of mass action is a mathematical ratio between the amount of products and the amount of reactants at equilibrium. So the bracket you know means molarity, and your coefficients in your balanced equation, for this example, the JKLM, your molarity of your products are raised to the power of your coefficient. So for the example, you've got C raised to the L power, D raised to the M, over A to the J, B to the K. So it's a ratio of the products to the reactants. If you know K, then you can predict the concentration of products and reactants. And if you happen to know the concentrations, you can solve for K. So we're going to solve a few really simple equilibrium problems using the law of mass action. When you use the law of mass action, you need to make sure that you do not include pure solids or pure liquids in what is called the equilibrium expression, the ratio of products over reactants. Since you're looking at molarity, which is a concentration unit, moles per liter, pure solids and pure liquids do not have a molarity. They don't have a concentration, so they're not going to be included in the equilibrium expression. When you get a K value, the size of that K will tell you whether the reaction produces mostly products or whether it doesn't go too far forward and creates mostly or leaves mostly reactants. The larger the K value, and by large, in terms of equilibrium constants, we mean greater than 1, you are looking at a mostly product-favored reaction. So at the end, since the ratio is products over reactants, if you have a greater concentration of products over a smaller amount of reactants, you will have a K greater than 1. You will be product-favored. So at equilibrium, you have mostly products. With the K less than 1, your reaction doesn't produce many products, so when equilibrium is reached, you have mostly still reactants. This is called a reactant-favored K value or reactant-favored reaction, where you still have mostly reactants. You haven't formed many products. So a K greater than 1 is product-favored. A and K less than 1 is reactant favored. So let's look at a simple equilibrium problem. The simplest version is to write the equilibrium expression. So looking at the balanced equation, you can see that I have the product ammonia, okay, squared because of the coefficient 2, divided by hydrogen cubed and nitrogen to the first power. So that's called the equilibrium expression. If on the right I plug in those values, so we know at equilibrium we've produced 0.001 molar nitrogen, 0.02 molar hydrogen, 0.005 molar ammonia. If we plug those values into the equilibrium expression and raise them to the power of that coefficient, we will get a number. Go ahead and pause and put those values in and calculate them. If you have calculated correctly, get a large number, 3,125. So this is a K much, much larger than 1. So at equilibrium, you have mostly products when this reaction has achieved equilibrium. So putting your values in and calculating, you should have gotten 3,125 for your K value. Let's look at another question. This time you need to write the equilibrium expression yourself, put in the molarities, follow the calculation format, pause the video while you're doing this. When you're done, you should have gotten 3.6 times 10 to the negative 3. If you got any of those other answers, you did not apply the law of mass action correctly. One last practice problem. So I've given you the answer already. You've got the equilibrium molarities. You've got the balanced equation. You should stop and check to make sure that you can get a K value of 42. You may also be able to solve for missing molarities or concentrations of substances at equilibrium. In order to do that, you have to be given a K value and all but one of the equilibrium concentrations, and then algebraically, you simply solve for the missing concentration. So we're not going to do this problem because you would need to be given a K value, but if given the values, you could plug in your molarities, raise them to the power of the coefficient, and then if given a K value, you could solve for the ammonia concentration. So we will work some of these in class. Le Chatelier developed a very simple qualitative approach to figuring out what's going to happen when you change a reaction that has established equilibrium. If you have a system that has already established equilibrium with the ratio of reactants to products, and you change something about that system, either adding or removing reactants or products, changing temperature, pressure, whatever you change, the system is going to try to undo that change that you did to it to try to reestablish equilibrium. So the system will reestablish equilibrium by undoing the change that you have imposed on it. So let's look at some examples. If you have the reaction at the bottom, A and B are reactants, C and D are products. If you add products, so if you add some C or D, you're going to shift the equilibrium that was established originally to use up the additional C and D. So if you established equilibrium between A and B, C and D, and then you add C and D, the reaction will shift to use up the additional C and D and try to establish a new equilibrium. If you remove the reactant A or B, then your reaction is going to shift to try to create more A and B. So the reaction will shift to try to undo what you have done to it. If you've reached equilibrium and you add a reactant, the reaction will shift to the right to try to use that up, and in the process will make more C and D. If you remove a product, either C or D, your reaction will shift to the right to try to create more of that product. This is how in industry they get an equilibrium reaction to produce more product. They remove the product as it's formed so the reaction cannot shift back and change the equilibrium. If you change the pressure of a reaction, now with this you have to look at only those substances that create pressure, so only the gas state of matter. So in this reaction you have 6 moles of gas A on the left and 3 moles of gas A2B3 on the right. So you're going to change pressure for gases by changing the container size. So if you decrease the container volume, think about your gas laws, volume goes down, pressure goes up. So if you're creating a stress of increased pressure, this reaction equilibrium is going to shift to the right to try to reduce that pressure by creating fewer moles of gaseous product, since there are 3 moles of gas on the right and 6 on the left. If you increase the container volume and reduce the pressure, the reaction will shift to the left to try to increase that pressure. So only gas molecules can affect the pressure. So when you're looking at changes of pressure, you're either going to shift away from more moles of gas to decrease your pressure or towards more moles of gas to increase your pressure. Changing temperature affects the rate of the forward and the reverse reaction. So it depends on whether your reaction is exo or endothermic. If your reaction is endothermic, where heat is a reactant, then you can think of adding heat as you would adding any reactant. So if you increase the temperature in an endothermic reaction, you're going to add more heat, so the reaction is going to shift to use up that heat, and in the process make more products. If you decrease the temperature of an endothermic reaction, the reaction will shift to the left, okay, to try to create more heat, and in the process you will reduce your amount of product and increase your amount of reactant. Exothermic reactions, negative delta H or heat as a product, again, if you increase the temperature, then you're adding that product heat, the reaction will shift away to try to use up that heat and reduce your amount of product and increase your amount of reactant. If you decrease the temperature of an exothermic reaction, the reaction will shift to the right to try to create more heat and in the process create more product C. So let's look at this reaction where we've got heat as a reactant, so it's endothermic. You've got a mole of gas on the left, 2 moles of gas on the right. So if we added N2O4, simply adding a reactant, we would shift the equilibrium away from the reactant side and create more product. If we add NO2, we're going to shift the reaction away from the products to create more reactants. Removing N2O4 will shift the reaction also to the left to try to create the product that you're removing. If you remove NO2, the equilibrium will shift to the right to create more NO2. Adding helium will have no effect on the reaction at all, as it is not in the reaction, it's not in the equilibrium expression, so adding anything that's not in the reaction will have no effect. If you decrease the container volume, so volume goes down, pressure goes up, you're going to shift to the fewer moles of gas, so that will shift the equilibrium to the left. If you increase the container volume, you will shift the equilibrium to the right. Because your pressure has dropped, you will try to increase that pressure by creating more moles of gas. And in this reaction, if you increase the temperature, since this is an endothermic reaction, increasing temperature will shift the equilibrium to the right to try to use up that additional heat. So we will work with the simple math of equilibrium and Le Chatelier's principle in class, and you will do a Le Chatelier lab, and that's about all we will do this year with equilibrium.